Hello everyone, welcome back to my channel. Today we are going to discuss the fourth part of P block elements of class 11. So question number 23. So far we have discussed 22 questions, right? So question number 23 is explain why is there a phenomenal decrease in ionization enthalpy from carbon to silicon. When we go from carbon to silicon, there is an increase in size. Size increases, at the same time shielding, or we can say screening, also increases. So as screening increases, size increases, so that electron, means outside electron, that is less attracted towards the nucleus. As it is less attracted towards the nucleus, it is easier to remove it, and that is called ionization enthalpy. So ionization enthalpy decreases. That's why there is a considerable decrease or phenomenal decrease in ionization enthalpy from carbon to silicon. It is already written because of the increase in size, atomic size, and screening effect, that both are increasing. And when they are increasing, the attraction for the outermost electron, see, the force of attraction of nucleus for the valence electron, that decreases. Okay, and that's why ionization enthalpy decreases from carbon to silicon. That is the simple reason. Okay, now question number 24, sorry. Now in question number 24, sorry, okay, in 24, how would you explain the lower atomic radius of gallium as compared to aluminium? So see, when we go from boron to aluminium to gallium, in a regular trend should be that there should be an increase in size. Okay, but see, the size of the gallium is smaller than aluminium. Why is it so? Because of the presence of 3d electrons in gallium, 10d electrons, 10 3d electrons in gallium. And the screening effect of 3d electron, screening effect of d electron is poor, and due to this poor screening effect, what happened? The outer electrons are more attracted toward the nucleus because shield is less. As shield is, nuclear charge increases, but shielding is poor, so outer electron is more attracted towards the nucleus. That's why size shrinks. Okay, it is written already that due to poor shielding effect of d electrons in gallium. So electrons in gallium experience great force of or strong force of attraction by the nucleus as compared to in aluminium. This is the reason that gallium is smaller in size, slightly smaller than that of aluminium. Difference is only slightly. See, this is 135 picometer and aluminium is 143 picometer. There is a slight decrease in size, but though it is slight, but it is not a regular trend. Otherwise gallium should be larger in size than aluminium, but as it is smaller than aluminium, so justification is simple, due to the presence of 10 d electrons whose shielding is poor. That's why effective nuclear charge is more, and therefore that it pulls the electron towards itself. Okay, and therefore size of the gallium is smaller, right? So this is question number 24. Now 25, question number 25, what are allotropes? Question is, what are allotropes? Sketch the structure of two allotropes of carbon, namely diamond and graphite, and what is the impact of structure on physical properties of two allotropes. We have already discussed in previous questions, but as the question is there, just try to understand what is allotrope. Allotropes are the elements, means different forms of element, different forms of same element. See, different forms of same element having same chemical properties. See, chemical properties are same, but physical properties are different because of different structural arrangements. Okay, okay, having same chemical properties but different physical properties due to their structures. Like diamond, in diamond each carbon that forms 4 bonds, single bonds with other carbons, and so on. Okay, there is network of covalent bonds, network of carbon carbon bonds, and that's why it is very hard substance, hardest substance known. Okay, it has high melting point because huge amount of energy is required to break those bonds. It has high density. Okay, and because it is hard, so it can be used as abrasive. Okay, so these are the functions of diamond. Because of the structure of diamond it occurs. Now come to graphite. In graphite, say each carbon that is attached to 3 other carbons and 1 electron is free per carbon. 1 electron is free per carbon. Okay, and that is existing in hexagonal layer structures, and layered layers have van der Waals attraction. See, there is 340 picometer distance between 2 layers. Okay, and due to this it is soft. Okay, one more thing, in diamond carbon is sp3 hybridized because each carbon form 4 sigma bonds, but in graphite each carbon is sp2 hybridized. It is soft, it is slippery because one layer can slip over other easily. It is soft and slippery, that's why it can act as dry lubricant. Okay, at the same time as electrons are free, therefore it is a good conductor of heat and electricity. Right, so see, in diamond carbon is sp3 hybridized. Diamond is 3-dimensional network solid, hardest substance, high melting point, high density. Graphite has layered structure and there is a van der Waals forces of attraction between the layers. That's why it is soft and slippery and can act as dry lubricant, can be used as dry lubricant where oil is not used. Okay, now come to question number 26. In question number 26, classify the following oxides as neutral, acidic, basic, amphoteric. Oxides are given. See, there are only 3 neutral oxides: CO, N2O and NO. They are not given, but keep in mind there are only 3 neutral oxides in chemistry, that is CO, carbon monoxide, N2O, nitrous oxide, and NO, nitric oxide. Okay, so CO is neutral oxide. Now non-metal oxides are basic. Okay, so carbon, silicon and boron, they are acidic oxides, B2O3, SiO2 and CO2. What about Al2O3? Though it is metal, but Al2O3 is an amphoteric oxide. Okay, PbO2 as well. PbO is basic, but PbO2 is amphoteric. Okay, and Tl2O3 is a basic oxide. Right. So next question is write suitable equations to show their nature. So CO, as CO is a neutral oxide, it does not react with acid as well as base at room temperature. Simple. Now B2O3, SiO2, CO2, they are acidic, so they can react with alkalis, base and form salt. See, boric anhydride B2O3 react with the sodium hydroxide to give sodium metaborate, SiO2 and CO2. They react with sodium hydroxide to give sodium silicate and sodium carbonate, okay, along with water. You know, when acid react with base, it gives salt and water. So same is the case here, okay. Now Al2O3 and PbO2 both are amphoteric oxide, that means they can react with acid as well as base. So see, Al2O3 can react with sodium hydroxide to give sodium metaluminate. Al2O3 can react with H2SO4 to give aluminium sulfate. PbO2 can react with sodium hydroxide to give sodium plumbate, or lead oxide can also react with sulfuric acid to give lead sulfate. That's it, okay. Now Tl2O3 being basic, it dissolves in acid to give TlCl3, okay. So we have to justify that if acidic oxide is there, then it will react with a base. Basic oxide is there, it can react with acid, or if it is amphoteric, it can react with acid and a base both. And if it is neutral, it will not react with acid as base. That's it. Done. Now come to question number 27. Question number 27 is, in some of the reactions thallium resembles aluminium, whereas in other it resembles with group 1 metals. So we have to support this statement by giving some evidence. So you know, if we talk about aluminium, aluminium uniformly shows which oxidation state? It shows oxidation state of +3 only, okay. It has only +3 oxidation state, okay. So like aluminium, thallium can also show, like aluminium, thallium can also show +3 oxidation state in some of its compounds like TlCl3, Tl2O3, see TlCl3, okay, Tl2O3, right, okay. And same like aluminium, aluminium, you know, can form the complex Al, octahedral complex AlF6 3 negative. On the same line, thallium can also form octahedral complex. So in this way, we have given the evidence that thallium resembles with aluminium. Now, due to inert pair effect, what is inert pair effect? Reluctance of or inability of s electron pair to take part in chemical combination. So due to inert pair effect, thallium can also show oxidation state of +1, and you know, alkali metals have +1 oxidation state. Alkali metals show, well, group 1 alkali metals, or we can say group 1 metals, they can show an oxidation state of +1 only, right. So thallium, due to inert pair effect, thallium due to inert pair effect show +1 oxidation state. That's why it can show +1 oxidation state in some of its compounds like Tl2O, even TlCl, TlCl4, okay, or even it form this Tl2O is strongly basic, just like group 1 metal oxides like Na2O, Li2O, okay, all of them, just like them, they are Tl2O3 is strongly basic. That's why thallium resembles with aluminium as well as group 1 metals. So that's all for the day. Thank you so much for watching this video. Do like, subscribe and share my channel. God bless you all. Happy learning. Jai Hind, Jai Bharat.